recording. That's shame on me. Apologize to the internet students who aren't present. Starting the recording now. Briefly reviewing what we've done for the first part of class is you were to watch the 2 videos I posted on squeeze theorem and how to show limit x equals 0 sine x over x equals 1. Now we're using that to calculate limit x goes to 0 of 1 minus cosine x over x. My first step was to multiply by 1 plus cosine x over 1 plus cosine x so as to get the numerator into the form 1 minus cosine x. Use a trig identity to transfer that into sine squared x. And then the suggestion was to use the limit laws and to break this up as sine x over x times sine x over 1 plus cosine x. And I really like that because the indeterminate form part of it, the sine x over x, we already know, that's known to us, to limit to equal to 1. And so the limit law works when you have a product where you know each limit. So I can write this now as limit x goes to 0 of sine x over x. And here's the product limit law. So this is a product, sine x over x times sine x over 1 plus cosine x. That's going to be equal to the product of the limits. So sine x over x times sine x over 1 plus cosine x. So this equation will be true because of the product limit law so long as both of these limits exist. And this one is known to exist because from our previous work, it's equal to 1. And this one I can figure out because sine x over 1 plus cosine x is a continuous function. All the trig functions are continuous. Quotients of continuous functions are quotients, just as long as all you have to check is the denominator there is not equal to 0. So just plugging in 0 gives me sine 0. So this is 1 times sine of 0 over 1 plus cosine of 0. Cosine of 0 is 1. So it's 1 times 0 over 2, which is 0. And so that proves that the limit as x goes to 0 of 1 minus cosine x over x is actually equal to 0. Of course, you can also verify this by taking the function y equals 1 minus cosine x over x, plugging that into Desmos, and then you'll see from the graph that you get that this definitely limits to 0 as x goes to 0, reaches down and touches the y-axis. Actually, I mean, I'll just show you that because we're all online, so I'll pull it up the Desmos right now. I think it's kind of nice to see mathematics 2 different ways, isn't it? So let's take y equals 1 minus cosine x. Well, I'll share my screen so you can even see me type it in. And I welcome you to do this stuff like this too when you're studying or like figuring something out on the homework. So it's 1 minus cosine x, quantity divided by x. And definitely you can't plug in x equals 0, it's not defined there, but you can look at where are the y values tending towards when x is close to 0. And if I zoom in here, you can see it, absolutely, it's true, the y values are tending towards 0 as x. As x gets close to 0. On the other hand, if you take those like secant lines, like for your, I guess you've got this, rough draft of the manuscripts due on Wednesday. So maybe it's worth stopping briefly and at least reminding you of that. Write your rough drafts. I don't care about a page limit, just looking at explaining the concepts, just giving you a chance to write in your own words. Mathematics is about communication just as much as literature or art is about communication, and give you some practice to communicate in your own words. So you'll write the draft, you'll submit it to me, and then you'll let someone else from class or someone who's taken the class previously, like if you know someone who took the class previously, or if you want to have one of the class or subject tutors. We've got like 4 or 5, we've got almost as many subject tutors for Calc 1 as we do students. So it should be no problem there to find like a partner to go over the draft. If you don't want to use someone from the class, contact Nancy Bonvillain for information on finding a subject tutor. And then you'll incorporate the feedback you get into your final draft. And so I'll be able to see your draft and then how it changes to the final project. And since you'll be talking about secant lines there, like if you took this function, for instance, and look at secant line from 0, 0 to like some other point, like 0 plus h to f of x plus h. One way to see what the tangent line is going to settle down to is like if you take any differentiable function, or like for us, don't worry about the word differentiable for right now, but like for most smooth functions like this, you want to figure out what the tangent line is, you can just zoom in on it. And the closer you zoom in, the more it's going to look like a straight line. And you're like, oh, okay, yeah, here's what the tangent line looks like. So calculus is all about like, how do we approximate a function on a very small scale using a line? It's one way to think about it. That's just food for thought. Like as you're writing this stuff, you zoom back out and the function gets all curvy and wiggly. I'm a little all over the place today, but let me pause for any questions or comments from you. Okay. So that's the theory part of it. The two things I want you to come away from this class knowing are definitely limit x goes to 0, sine x over x equals 1, limit x goes to 0, 1 minus cosine x over x is 0. I'd like you to know how to demonstrate both those things. I'd like you to know that sine x over x, that limit comes from the squeeze theorem. And check out my video on demonstrating the inequality that cosine x is going to be less than or equal to sine x over x. And also this demonstration of how you can use that and the limit laws to then arrive at the conclusion, limit x goes to 0, 1 minus cosine x over x equals 0. So the result is kind of clear and straightforward that these two limits exist, and there they are, but there is a process there of mathematical reasoning that I do want you to have some accountability for being able to track through. But for the rest of class, let's do some problems. So I want to look at this first example, and this example came up in like a extra credit homework problem. But now I will promote it fully to something that we talk about on the board. So say you want to look at something like limit as x goes to 0 of sine 4x over x. And you know the limit sine x over x, but you don't know the limit sine 4x over x. So how might you approach this? And one way you might do it is you might just graph y equals sine 4x over x and just kind of investigate what does the graph look like as x goes to 0. You might also do a numerical exploration, just plug in some numbers, x equals 0.1, x equals 0.01, see if the limit is tending towards anything. There's also an algebraic way we can do this and really cleanly get an answer using the fact that sine x over x limits to 1. And here's the trick. It's this mathematician's trick of multiplying something by the number 1. And in this case, I'm going to write 1 is equal to 4 over 4. And the reason why I like this is because now you've got limit as x goes to 0 of, well, on the denominator, I've got 4x. And in the numerator, I've got 4 times sine 4x, but I'm going to put the 4 out here. And in fact, there's this limit law that says if you've got a limit of a constant times a function, then that's equal to constant times the limit of a function. Which makes sense for sure. Like if the limit of x is equal to L, then you would reasonably expect the limit of 4 times x to be equal to 4 times L. That's what this constant limit law is saying. So we've reduced the problem now to figuring out what's the limit as x goes to 0 of sine of 4x over 4x. And based on what you know so far, does anybody have a guess of what you expect that answer to be? Like, what do you expect limit as x goes to 0 of sine 4x over 4x to be, perhaps, if you'd like to volunteer? So for me, I'm thinking, well, I know that if I had sine something over something, then as that something goes to 0, the limit is equal to 1. And that's making me think, well, maybe I could make a substitution, like y equals 4 times x. And now I've got 4 times the limit. X goes to 0 of sine y over y. And certainly the limit as y goes to 0 of sine y over y is equal to 1, so we know that. But I have to ask my question, like, what happens to y as x goes to 0? But if I look at this equation, I can look at this and sort of use my intuition and say, look, well, as x goes to 0, it's certainly true that y is going to 0 as well, using this horizontal arrow to indicate that the limit of 4x is equal to 0 as x goes to 0. Or in other words, as x goes to 0, y tends towards 0. And so that's going to let me say, look, like this is equal to the limit as y goes to 0 of sine y over y. That's what made the substitution kind of legitimate. Like initially I've got x goes to 0, and I want to replace, 4x with y. And so I did that. And in order to put everything in terms of y, I just have to ask myself, as x goes to 0, what's y going to? And my new variable is also going to 0. So my new variable is going to say, limit as y goes to 0, sine y over y. And this is known to me to be equal to 1. And therefore, the answer is 4 times 1, because I pulled out that constant. So all that to tell me that limit as x goes to 0, and you saw this with your numeric investigation if you did this extra credit problem. But this is like a little bit more formal, like sine 4x over x limits to 4 as x goes to 0. So sometimes you can get away with using a limit that you already know, like sine y over y as y goes to 0. You can use it to calculate something like this. If you do this trick of first multiplying by 4 over 4 to get the numerator and denominator to match, and then saying, well, what about x goes to 0 instead of 4x goes to 0? But if x is going to 0, then 4x is also going to 0, so it's no problem. You can calculate this, and it works out. So that's a little bit informal in my description. Like once again, you take that Math 312, that analysis class, and we'll be more formal in our definitions and our proofs and demonstrations. But Calculus 1 is not about focusing on the formal proofs quite as much as focusing on the intuitive explanations and figuring out how everything's working. So the level at which I'm writing on the board is the level at which I'll ask you to be able to argue. Okay, let me give you a practice problem to do. This is section 2.6, number 3, if you're following along. I'll give you a minute to work on it, and then I'll show my solution. The instructions say, please use the squeeze theorem to calculate the limit. So calculate limit as x goes to 1 of x minus 1 times sine of pi over x minus 1. So some remarks on this. First of all, you can't evaluate this by simply plugging in x equals 1, because you'll end up with sine of pi over 0, which is undefined. So instead, you might try using the squeeze theorem. So can you find two functions, so x minus 1 times sine of pi over x minus 1 is going to be your like your middle function. So what two functions on the outside, like above and below, can you figure out? And so my hint to you is that sine of anything is going to be less than or equal to 1 and bigger than or equal to -1. So let me give you half a minute to work on that. You can use the squeeze theorem to evaluate that limit. So after giving you some time to think on it, let me show you the way that I might approach this. The way I like to approach these problems is Here's the thing that's giving me trouble, because when I plug in x equals 1, I get undefined. So I want to figure out, like, is there an upper bound for this? Is there a lower bound for this function? And yeah, there totally is. For the trig functions for sine and cosine, you know, or at least I'd like you to remember for this class that those functions are bounded in between -1 and +1. And it doesn't matter what the argument of sine is. Sine of whatever has no choice but to be less than or equal to 1, bigger than or equal to -1. That's because of the way that sine is defined. You use the unit circle, and like whatever this angle is, doesn't matter, because sine of x is always going to be this y value, which can't be bigger than 1, can't be smaller than -1, because of its relationship to the unit circle. So now that you've got this fundamental identity, what you want to do is you want to think of multiplying through by x minus 1. So you just want to take minus x minus 1. And this identifies for you your three functions. This is really your L, this is your F, and this is your U. And you might quibble with me a little bit, because you might remember that if you multiply an inequality by a positive number, it's preserved, but if you multiply by a negative number, then the inequalities switch. Might be me thinking about that. So this is valid if x minus 1 is bigger than 0, which would mean x is bigger than 1. So that would be like taking a limit from the right. And like if you say that, then I can say, yeah, that's valid. But it's also true that I could just take, the squeeze theorem works for right-handed limits. So I could just take the limit as x goes to 1 from the right, only considering values that are bigger than 1, so that x minus 1 is bigger than 0. I could look at minus x minus 1. It's going to be less than this limit in the middle. It's going to be less than this limit. On the other side. And these limits here, they're equal to each other. As x goes to 1 from the right, you get 0 on the left and 0 on the right, which tells you finally that, I'll put it up here, it tells you finally that the limit, so x goes to 1 from the right, of x minus 1 times sine pi of x minus 1 is equal to 0. And just like the band's journey, you're like, whoa, you're halfway there. If you can calculate the limit as x goes to 1 from the left, and also show that it's 0, if the left and right-hand limits match, then that means the limit itself must also be equal to 0. So you could just do another argument. So you could say, like, what if x minus 1 is less than 0? And then when you take this inequality and multiply through, both inequalities will flip. So let's see that. So I get now x minus 1 times minus 1. So it's the same thing as before, but now this is negative because x is less than 1. And so the inequality will slip. So this will be bigger than or equal to x minus 1 times sine of pi over x minus 1, which will be bigger than or equal to x minus 1. But the thing you see here is that nothing really changed. It's just your upper and your lower function switched. That's all. And so you still do the limit law, or the squeeze theorem, excuse me, and you dutifully write out that, like, as x goes to 1 from the left, this will be bigger than the limit of the middle part. Be bigger than the limit x minus 1. So that left-hand limit by the squeeze theorem, limit as x goes to 1 from the left is equal to 0. This limit's equal to 0. And so the limit of the inside function also equal to 0. So you get the corresponding conclusion. So it's a little bit, I mean, if you're not used to arguments that take 5 or 6 or 7 lines, then it's maybe a little bit frustrating to write down, but ultimately not that too bad. So you conclude that the left and right hand limits are both equal to 0, and therefore the limit itself is equal to 0. So certainly the question would have been more straightforward if we only had to calculate one of the one-sided limits, but it's just the nature of what we were being asked. If we multiplied by a negative number, it would flip the inequalities, but it had a minimal effect on the actual argument. Just made us kind of redo it. So any questions or comments on that? When you're turning something in for homework, my board work is not quite as good as what I would do for homework when I have time to sort of sit and think and write it on the paper. I think breaking it up into the two cases, demonstrating the left and right hand limits with the squeeze theorem is very good. You might also include 1 or 2 sentences, like in English, describing what you're doing and why. That'll just make it clear for a reader who's evaluating your work. So just like a small note on that about the homework. Let's sneak in one more problem from the textbook before we go. This will be number 28. This will be similar to our other trigonometric limit that we did using that sine x over x going to 1 business. So this is number 28 from chapter 2.6, if you want to follow along. We're being asked to compute limit as t goes to 0 of sine of 7t divided by sine of 11t. And at first you might not think this has anything to do with what we've been talking about, but they do give you a hint, and it says the hint says multiply numerator and denominator by 7 times 11 times t. So in other words, multiply by 7 times 11 times t divided by 7 times 11 times t. So they want you to employ the mathematician's trick of multiplying by 1, and this is how you represent the number 1. Then can you rearrange this fraction in such a way that you recognize what the limits are going to be and then use the limit law? Let me give you a minute to work on that, and then I'll show you my solution. And of course, private message me any question if you want to talk it through. After giving you a minute to work and think about it, I'll see if I can complete this in the remaining few minutes. So I'll follow the hint, and I'll multiply numerator and denominator by 7 times 11 times t. So definitely this didn't change the value of the limit because I just multiplied by the number 1. But now can I rearrange the terms into something that I can use the limit laws with? And what I'm seeing is if I take sine 7t over 7t and sine 11t under 11t, then those are groupings that might work out for me. So it looks like I can take out, well, first of all, let's do limit as t goes to 0. It looks like I can, I want to use this 11t and I want to use this 7t, so it looks like I have 7 over 11 left over. And then I've got sine of 7t divided by 7t, and then I've got 11t divided by sine of 11t. So I've simply rewritten this now as a product of 3 things. And I want to use the limit law now, which says that the limit of the product is the product of the limit. So this is going to be 7/11, just pulling out the constant, which is fine, times limit as t goes to 0, sine 7t over 7t times limit t goes to 0 of 11t over sine 11t. And I've already argued before that if I've got sine 7t over 7t as t goes to 0, I mean, that's the same thing as 7t goes to 0. So this is going to be 1. This one you might be a little concerned about, so I'll show some more steps for that one. You might be a little bit concerned about this because it's 11t over sine of 11t. Check for comments. Yeah. So how do you handle that? Well, here's my idea for that. This is the same thing as 1 over sine 11t over 11t, right? I can rewrite this fraction improperly as 1 over sine 11t over 11t. And then the limit law tells me that if I have a function, the constant 1 divided by something else, then the limit of that, the limit of the ratio is the ratio of the limits, provided the limit of the denominator is not 0. But this limit is going to be equal to 1 because it's sine y over y with y going to 0. Like 11t is going to 0 since t is going to 0. So this is going to become 1 over limit as t goes to 0, sine 11t over 11t. So all that to say, this is still the number 1 because it's 1 over 1. So if you were writing that down on homework, you might get here and you might put like a little note that I'm going to calculate this in the next line and then explain this and then, proceed further. But this one we've calculated to be equal to 1. So the limit is 7/11 times 1 times 1. So this limit, sine 7t over 11t, is actually equal to 7 over 11. As t tends towards 0, the y values of that ratio tend towards 7/11. So that's pretty cool. So that's an example of how to argue using the limit laws and the fact that limit of sine x over x as x goes to 0 is equal to 1. Okay, any final questions or comments for me? So let me know if you prefer more theory explanation in class. Like I could have spent more class time today showing you the inequality cosine theta less than or equal to sine theta theta less than or equal to 1. Instead, I had you watch the video and chose to spend more time working problems in class. But if you prefer more theory, then let me know. We can do some more theory days. Certainly want to arrange the class in a way that's going to be helpful to you, my students. So you can just think on that and let me know. And let me know if you have any questions or comments. We've got office hours from 3:30 to 5 today. And other than that, have a great day. I'll see you on Wednesday.